Hello everyone, I am Dr. Rajesh and today in this lecture we will study this important problem based upon the Gauss divergence theorem. Evaluate this particular surface integral where f is the vector field given by this expression. S is the surface of rectangular parallelepiped having the dimension along x-axis this one, y and z. So we have to evaluate this one. So firstly let me draw that parallelepiped, that what this parallelepiped will look like. Say we have, since it is a rectangular parallelepiped, so we have to make sure that sides don't look equal. So this is the rectangular parallelepiped and these are the rectangular axes. Say this point is O and this is x-axis, this is y-axis and this one is z axis. Okay, so these are the axes. See the dimensions given. X is from 0 to a, so this is a length. Along x-axis this is a. So if I say that this length is a, this will be a, and along y-axis it is given to be b, and along z-axis this is given to be C. So now let me put the positions of these points. So let me first name these points. So these points can be named in any symmetrical manner. So manner we are following is anti-clockwise, C, D, say E, F, G. Okay, so these are the points. So now let me write the coordinates of the points. So for this point, the coordinates are, it will be a comma 0. This point is on, G is on y-axis, so the coordinate will be 0 comma b comma 0, and this point is in x y plane, so z is 0, so it will be having the coordinates a comma b comma 0. Now see this point f is in z y plane, so x is 0, so this will be having coordinates 0 b comma c. Now look over here, this point c, this is in xyz, this is in the outer outer direction, so this is in xyz all, so this will be having all the three coordinates a b c. Now look over here, this point o is origin, so its coordinates will be 0 comma 0 comma 0. And what will be the coordinates for d? D is in z and x, so y is 0. So now let me fix the coordinates for this one, a comma 0 comma c. Now let me fix the coordinates for this point, e. E is on z axis, so its coordinate will be 0 0 c. So now I think every point has been covered. So these are the coordinates of the points, and these are 8 points, and there are 6 faces. There are 6 faces. One is this one, and other at the back 2, this 4, and this, and top 6 faces. So now come back to the problem. The problem is only to evaluate the integral. So now it is our discretion to either evaluate this surface integral, or we can use the divergence theorem, and that provides us an important tool to convert this surface integral into volume integral. But this surface integral, as we will try to solve, will contain the six faces. This face, this face, these six faces it will contain. So it will be quite cumbersome to solve that surface integral. So it is always advisable to use the Gauss divergence theorem. So now let me write the statement again of the Gauss divergence theorem. What does Gauss divergence theorem states? That it states that surface integral over the surface S and the normal component of the vector field is equal to is equal to the volume integral of divergence of vector field F over the volume integral having region R. So this is the region R. So if I say this F is a vector field, so I can denote this vector field in this as these are the say components of vector field. This is the vector field all over the parallelepiped. So these are the elements of vector fields. So this is the vector field. So now we see if we have to calculate this surface integral, so it will be enough to calculate this integral that is given by Gauss divergence theorem. So now the divergence of this particular vector field is given by further equal to, this is further equal to triple integral, and divergence is with respect to x. This with respect to x, this is constant quantity with respect to x, this will be 2x. This will be 2x. Okay, and plus it will be plus. Now with respect to y, it will be 2y. This is constant quantity, so this will be 2y. So this will be 2y, and here is plus, and with respect to z, here with respect to z it will be 2z. This will be constant, so this will be 2z, and the volume integral over the parallelepiped R. Now we shall, since we know that this volume integral V consists of small volume elements given by, this is dx, and this volume is given by this dx, dy, dz, and this whole parallelepiped is composed of these small volume, infinitesimally small volume elements. So now I'm going to put the limits for, here I'm going to put dv is equal to dx, dy, dz. So this will be equal to, this will be 2x, 2y, 2z, and this will be dx, this will be dy, and this will be dz. Now what are the limits for x? Limit for x is from 0 to a, because on x-axis it is changing from 0 to a. So this will be 0 to a, limits for x, and limits for y will be 0 to b. So it will be 0 to b, and limits for z, this is 0 and this is c, so it will be 0 to c. So limits for z will be from 0 to c. So this needs to integrate. Now firstly, because these limits are constant. Look over here, these limits are both lower and upper limits in all the three integrals are constant, therefore they can be solved in any order. So firstly, if we have written x, so we can integrate with respect to x, we don't need to change the order. We need to change the order in case of if any of the limit is variable, then that limit is solved first. So here all the limits are constant, so I'm going to evaluate with respect to x first, and limit is written from this one. When I will be integrating with respect to x, I will treat y and z as constant. So this integration will be equal to, this will be x square by 2, here is 2, plus this 2 is constant, y is constant, and 1 is integration of 1 is x to z, and this will be x, and limit is from 0 to a, and here will be dy, limit is from 0 to b, and here dz, limit is from 0 to c. So this 2 will cancel out, this 2 will cancel out, so we will get the integrals put over here. When a will be put over in place of x, we will get, this will be a square plus 2y a plus 2z a, and this is dy, limit is from 0 to b, and this is dz, limit is from 0 to c. Now we need to integrate with respect to y. So this will be further equal to, this is 0 to c, and when we will be integrating with respect to y, we will treat z as a constant. So here it will be a square y plus 2a y square by 2 plus 2az y, and limit is from 0 to b, here is dz. So this is further evaluated as 0 to c, and this will be a square b, this 2 will cancel out, this will be ab square, and this is plus 2ab, there is z. So this is with respect to z. Now with respect to z will be a square b z, ab square z plus 2ab z square by 2, and limit is from 0 to c. So this will be further equal to a square b c plus ab square, this 2 will cancel out, ab square c plus ab c square. So abc from here can be taken outside, abc, so this will be ab plus c. So this is the required value, therefore the required value is this one. So in this lecture we have seen that using the Gauss divergence theorem have made our task very easy. Otherwise, it would have been very cumbersome job to calculate this surface integral. But with the help of divergence theorem, we have switched from surface integral to volume integral and very easily calculated its value. So this is one of the tool that Gauss divergence provides us to switch between the surface integral and volume integral, and that we have seen in this particular lecture. So that's all I have from this lecture. If you have liked the lecture, please like, subscribe, share and comment. This is Dr. Rajesh saying you goodbye. Take care. Bye bye. See you soon. Thank you very much.